Hi there everyone, how's it going? Terry Brown Mechanical Engineering here to go through another engineering mechanics video problem. So let's get into it. So this is the problem this time. So it's a frame and machine problem. So in this case it's a frame because the components can't move relative to each other. It's just supporting a static load. Okay, so whether you can identify whether it's a frame or a machine doesn't really matter too much. As long as you apply the principles and fundamentals of engineering mechanics, drawing free body diagrams, applying your equations of equilibrium, you should still be able to solve the problem. First thing to do is to draw a free body diagram. So I've indicated here that I'm going to draw a free body diagram of the member AB here. And what I'm also going to do is draw a free body diagram of the pulley and the member BC, just to show you what goes on with the forces of interaction between the various components of this frame. So the question's asking us to determine the force acting on each of the members of the frame. Now you could start with a free body diagram of the whole frame if you like, doesn't really matter, but this time I'm going to start with a free body diagram of AB. So draw that in, make it nice and neat. Put your dimension lines going to the point that they're actually referencing, not off somewhere out here. Make it nice and neat and clear so that it's easy for you and others to read. Right, so usually the best place to start is with your applied loads. Now, as you can see on my free body diagram here, I've put 400 and 400 at this endpoint where the pulley is attached. So you may or may not understand why I've been able to do that. So I'm just going to go through that in a second. But before that, let's have a look at some of the other things. So here I've drawn a line along the line joining B to C. And the reason that I've done that is because I can see that this link here, BC, is a two-force member in equilibrium. It's attached at only points B and C. And if we assume that the weight of the component itself is negligible, then there's only two places where forces are applied. So those two forces must be equal and opposite and collinear, so therefore it's a two-force member. So we can put in the force along the direction or along the line joining BC, and then just label our unknown RBC here. So we'll work out its sense in a second. So just noting here that BC is a two-force member in equilibrium. Then moving over to drawing our reactions at point A. We have a pin connection at A, so we know we'll have two components, two orthogonal components of reaction force, and usually we'll look at the horizontal and vertical components. As I said before, they don't have to be horizontal and vertical. You can put them in any orientation you like, but usually the most convenient is to have them vertical and horizontal. The other way you can represent this, of course, is to say that there's a reaction force here with an unknown direction. All right, so over on my force RBC here, I've put an arrowhead up to the right. How have I worked that out? By imagining that I'm taking moments about point A, this force here, the 400 Newton force on the right, is tending to cause a clockwise rotation about point A. So therefore, for this beam to be in equilibrium, this force needs to be pushing upwards. So it must have a vertical component. So therefore, this is upwards and to the right. The 400 Newton horizontal out on the end here, that has no moment about point A, so that doesn't come into consideration. But it does when considering what to put on our forces over here at A. So thinking about what sense is this force going to be, we can look at our other forces that we've determined, RBC upwards to the right, assuming that you've got this one right, and then we've got a 400 Newton force acting to the right at the end, so therefore this one has to be to the left. If you can't go through that thought experiment prior to putting on arrowheads on your reaction forces, then just assume a sense for the forces, and then your equations and algebra will tell you whether you got it right or not by the fact that if you got this wrong, then the answer will come out as negative in your algebra. And as I say, every time, if you get a negative answer for one of your forces, don't go back and change the free body diagram. Right? Just leave it as it is. Because if you change the arrowhead on your free body diagram, then your equations are wrong. Right? Or they don't match what is on your free body diagram. Right? Best to just carry on, and then when you need to, or if you need to, substitute the negative value into the equation that's been written according to the arrowheads that are showing on your free body diagram. Right, so then looking at the vertical component, RAY, we've got RBC acting upwards, 400 acting downwards, so we can't easily determine whether it needs to be up or down from some of the forces in the vertical direction. So let's think about another way to work it out. If we take moments about point B, then we've got the 400 Newton vertical force out on the right tending to cause a clockwise rotation. So therefore and then the only other force that will have a moment about point B will be RAY. So therefore it also has to be acting downwards in order to create an anti-clockwise rotation. So there's my free body diagram, and I can start writing equations of equilibrium for that. Right, before we start writing our equations of equilibrium for the free body diagram of the beam AB, let's have a look at the free body diagram of the pulley and see how we ended up with these two 400 Newton forces acting at the center of where the pulley is attached, rather than the rope that we've got on the original diagram. Right, so if we draw a free body diagram of the pulley, circle to represent that, and just indicate that its radius there is 0.2. It's given in the diagram above. And at the top here, we've got our 400 Newton force acting. Right, so this pulley needs to be in equilibrium. So for it to be in equilibrium, we've got the rope attached on the other side, and we've also got the pin force at the center of the pulley. So we're assuming that the pulley is free to rotate. Right? If we disconnected the rope down here and pulled here, that would just freely rotate. Okay, so there's a force generated in the other side of the pulley here, and you may or may not know that it's acting downwards. Doesn't really matter. If you put it upwards, then if we get a positive answer for showing the force acting downwards, then you'll get a negative answer for showing it acting upwards, which tells you that you've got the force in the wrong sense. Right? So there's our tension in the cable or the rope. Let's just call it T for now. And if we take moments about the center of the pulley, let's label it with label O. And say some of the moments about point O, anti-clockwise positive equals 0. We have the force, unknown force T in the cable, times the radius R, tending to rotate anti-clockwise about point O, so that one's positive. And then we have the 400 Newton force up here, times R, tending to rotate clockwise, so that's negative, all equal to 0. So the R's obviously cancel out, and rearrange that, and we get T equals 400. So in the past, we've just said, assume the tension in the cable is constant throughout the cable, right? Or you may have just used that in high school or physics or whatever. But here is the engineering mechanics proof of the fact that the force or the tension in the cable is constant throughout the cable. And then, of course, at the connection at the axle of the pulley, we've got a pin connection, so horizontal and vertical unknown reaction forces. Hopefully we can clearly see that a vertical force equal and opposite to T, so let's just call that ROY for now, and then horizontal force equal and opposite to the force applied at the rope, and call that ROX. And then if we do our equilibrium equations, you can there justify what most of you should be able to see just by looking at the free body diagram. All right, what about now the free body diagram of the link BC that we've said is a two-force member? So if we draw that, because point C and B here are the only places where forces are applied, assuming that the weight of the link is negligible, then these forces must be equal and opposite and collinear. Right, so what direction do we put on this, or what sense? So we already know the direction. What sense do we have it up to the right or down to the left? Right, if we go up and have a look at our other free body diagram up here, right, the free body diagram of the horizontal beam AB, at point B, we've got an action-reaction pair of forces. So what's happening up here on AB, down here on CB, must be equal and opposite to that. So up on the free body diagram of AB, RBC that we've shown here is the force that the link CB exerts on this beam AB. Whereas down here on the free body diagram of the link BC, force that we have here is the force that the beam exerts on the link. And then down here at C, we need for that to be in equilibrium, sum of the forces equals 0 along this line, so equal and opposite, so that must be acting up to the right. And we can label with those all with the same label because they're all the same force. And of course, acting on the support here at C will be equal and opposite to this force down the bottom left here, RBC, that I've shown. Right, so you need to obey Newton's third law when drawing the components separated. Also, looking back at our free body diagram of our pulley and looking at the right hand end of the beam AB where the pulley is attached. So where I've got 400 horizontal and vertical at the center of the pulley there now on my free body diagram, that comes from equal and opposite of the forces at point O that we determined on the free body diagram of the pulley. Another point to make is that what I see a lot of students do is to put forces on your free body diagrams while things are still connected. Okay, that is wrong. Do not do that. Because at that location, right, it's not just these forces that exist. Here we've got both this force and this force acting against each other while they're still connected. All right, so if anything, right, you should put that, right, to be correct, right? But we don't do that, right? And no, I don't think I've ever seen any student do that. What I do see them do is that, which is wrong. Don't do it. Right, so now let's start looking at the equations of equilibrium for our beam AB, taking moments about the point where two of our unknowns pass, and that's point A. So indicate here some of the moments about point A, anti-clockwise positive equals 0. Start looking at each of our components. So we've got RBC here, so we'll need the vertical component of this. I've recognized that from this geometry that this little triangle here, CB and the link shape, will be a 3-4-5 triangle ratio. If you didn't recognize that and calculated the angles, that's fine. You can do that as well. Doesn't really matter. So if you're not comfortable or familiar with doing this, then by all means do inverse tan of opposite over adjacent. So inverse tan of 1.5 over 2 meters will give you, this angle here that you can see down in the bottom left. Okay, so here this will be 3/5 RBC for the vertical component, acting at a distance of 2 meters, tending to rotate anti-clockwise about point A. So therefore that's positive, so we can move on to the next one. 400 Newton force acting vertically downwards, perpendicular distance of 4, tending to rotate clockwise, so that'll be negative. And they're the only two forces causing a moment about point A. This horizontal force over at the end here, its line of action passes through point A, so therefore it doesn't cause a moment about A. Right, so we can put all that equal to 0, rearrange and solve for RBC. round it up to 3 significant figures and convert it to kilonewtons. Then we can look at our other equations of equilibrium. Sum of the forces in the vertical direction equals 0. So minus RAY plus the vertical component of RBC, 3/5 RBC minus the 400 equals 0. Do your maths to get RAY equals 400 newtons. And then sum of the forces in the horizontal direction equals 0. We have minus RAX plus the horizontal component of RBC, so 4/5 RBC, plus the 400 Newton force out on the end there, all equal to 0. Substitute in for RBC that we calculated up here and solve for RAX. And find the resultant of the force at A, which will be 1.52 kilonewtons, and resultant of the force at R at point O, at the center of the pulley, 0.57 kilonewtons. And so indicate there our final answers, rounded up to 3 significant figures. So force on the beam at B is RBC, which is also the force on the link BC at both ends. Then we have the total force at A, connection at A on the beam, so that was 1.52 kilonewtons, and the force on the beam and on the center of the pulley at the end, right end here, is 0.57 kilonewtons. Okay, so that's the end of the problem. You probably should go and do some checks just to make sure that you got your answers right. Maybe take moments about somewhere else. Let's see, let's take moments about point B and have a look at our answers. So if we take moments about point B, we can see RAX, the 400 over here, and RBC all pass through point B. They all have a 0 moment. So we're left with the 400 out to the right, causing a clockwise moment, 400 times 2, and we have RAY out to the left here, causing an anti-clockwise moment about B, RAY times 2. So therefore, RAY must be equal to 400. So just do a quick check of your solution in that way. The other thing you could do, if you know your 3 force members in equilibrium, you know that if there's 3 forces acting on a body, then those 3 forces must be coincident at a point. So if we can continue the line of action of this force there, somewhere like that, this one, the line of action of the force at where the pulley is, will be at 45 degrees. So that's there. So therefore, we know the line of action of the force from A must intersect, or must pass through that intersection. So that shows us that RAX must be a fair bit bigger than RAY. Okay, so maybe twice the size of RAY based on that angle. So what have we got here? RAX is 3 times. Okay, so that's probably about right. I'm not sure whether I've drawn this particularly, so it's just gives you a feel for whether you've got things in the right direction or not. Right? If you had RAY acting upwards, for example, then you know you've got something wrong, definitely, because the line of action of the force, resultant force at A, right, if RAY was acting upwards, would be out this way. Okay, so it's not going to intersect the lines of action of the other 2 forces. Okay, so doing those checks doesn't guarantee that you got the right answer, but it helps to give you confidence that that you've done the right thing. If you had have calculated, for example, the wrong angle in here by a few degrees, then that's doing these checks is not going to tell you that. But it makes you go back and look at your solution and think about it a bit more, and then you might pick up a mistake that you've made. All right, that's the end of the problem. Hopefully that was helpful and cleared up some things about how to draw free body diagrams for when you separate frames and machines, how the forces interact between connecting bodies. It's really important to get that right, because if you don't, when you get to the harder problems with more members that are connected and you need to carry forces that you calculate from one free body diagram into the next one, you won't be able to get the answers correct if you're not careful about how you draw your free body diagram, with being consistent, not changing your arrowheads as you go through, and so on. All right, so anyway, I'll leave that there for now, and I'll catch you in the next video. Bye.